All right. Hey, everybody. Welcome back. We've got a short video for you here. We are going to introduce a new kind of series, something called a p-series. And so far, the only real series that we've introduced by name is the geometric series. So the p-series is our second big class of series. So goals for this video: identify what a p-series is, and be able to identify when or whether a p-series converges, right? So what are some properties that we can look at to see if Okay, so first of all, a p-series definition. P-series is a series that takes this form up here. So the sum, as n goes from 1 to infinity, of 1 over n to the p, where p is a constant number. So the p in p-series is this exponent that's being attached to n, right, where n is allowed to range from 1 up to infinity. So a couple sort of quick and easy examples here. Notice if p is equal to 1, then our sum is just the sum as n goes from 1 to infinity of 1 over n to the 1, right? And so that's just, 1 plus a half plus a third plus dot, 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 right? That is just going to be our good old friend, the harmonic series. Ooh. Okay, so the harmonic series is an example of a p-series, specifically when p is equal to 1. If p is equal to 3, let's say, then we would get the sum as n goes from 1 to infinity of 1 over n cubed, right? And okay, that would just be 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed, and so on and so on. Right? So this would be another example of a p-series, this time with p equals 3. So that's all that a p-series is. Now let's see when a p-series converges and when it diverges. We've already seen that the harmonic series diverges. So we know that at least some p-series will diverge. However, a good number of them will actually converge. And we get the following claim, which we're going to prove here in a moment. We're going to claim that a p-series converges if and only if our p-value is bigger than 1. That if and only if means that not only will it converge if p is bigger than 1, but those are the only cases where it converges. Or in other words, if p is less than 1 or if p is equal to 1, the series diverges. So let's try to prove this. First of all, I'm going to show you what happens if p is less than 0. So if p is less than 0, our terms are of the form 1 over n to a negative number, right? So if p is negative, then the terms of our series look like 1 over n to a negative number. And because that's a negative number, I can rewrite that as n to a positive number. And as n goes to infinity, right? As n goes to infinity, these terms right here will just keep getting bigger and bigger and bigger. In other words, the terms themselves will not converge to 0. And as a result, the series itself will diverge by the test for divergence, right? So this will actually diverge. The series will diverge. That's what happens if p is less than 0. If p is equal to 0, so if p is equal to 0, sort of copy from above, our terms will be of the form 1 over n to the 0, and 1 over n to the 0 is just 1 over 1. So our individual terms will all be plus 1. Sorry, 1 second here. Okay, sorry about that. So what we see here, right, is that regardless whether or not p is less than 0 or whether or not p is equal to 0, we see that the individual terms in our series will either take the form n raised to a positive constant or will just be 1. Either way, they're not going to 0. And so by the test for divergence, our overall series must diverge. Now, the more interesting case is what happens if p is bigger than 0. So if p is positive, what we'll see is that we can, the individual terms will go to 0. So we cannot use the test for divergence, but we can use the integral test. We can use the integral test, and we can compute the integral from 1 to infinity of 1 over x to the p dx, right? 1 over x to the p is a continuous decreasing function that can be used to represent the series 1 over n to the p, or at least can be compared to the series 1 over n to the p. So we've seen from the integral test that the series will converge if and only if the integral converges. And so let us compute the integral here. Because this is an improper integral, we have to take the limit as b goes to infinity of the integral from 1 to b. And I will rewrite the 1 over x to the p as an x to the negative p. So that integral, right, we'll take the antiderivative. We'll keep this limit out front. Limit as b goes to infinity. We'll take the antiderivative. So that's going to be x to the negative p plus 1, x raised to the negative p plus 1 divided by negative p plus 1 from 1 to b. And that's just going to be the limit as b goes to infinity of, we can plug in here, this will become a b to the negative p, the negative p plus 1 over negative p plus 1 minus 1 over negative p plus 1. Okay, so we've computed the improper integral. We've gotten this as our answer, and now we just have to take the limit as b goes to infinity. And if our limit converges, that means our integral converged, which means that our series converges. So the question becomes, when does this limit actually converge? When does this limit make sense? And it turns out that it depends entirely on this exponent up here. If the exponent is positive, then b will get bigger and bigger and bigger. B raised to a positive exponent will get bigger and bigger and bigger. And so this whole thing will diverge if the exponent is positive. But if the exponent is not positive, right, if the exponent is negative, then what we'll see is that as b goes to infinity, we'll get a bigger and bigger and bigger number raised to a negative exponent. That will make this whole thing smaller and smaller and smaller, and so the integral will converge, right? This piece will converge to 0, and the whole thing will converge. So the entire problem, I guess, whether or not the series converges, whether or not the integral converges, hinges on that exponent, and specifically, we need negative p plus 1, that exponent, to be less than 0, which means that we need p to be bigger than 1, which is exactly what we were trying to show. Now there's this edge case, right, of what happens if p is equal to 1. In that case, though, we have our old friend, the harmonic series, and we have shown that the harmonic series definitely diverges. So there you have it, new class of series, the so-called p-series, and we now know that a p-series converges if and only if p is bigger than 1. All right, that's it for this time. I'll see you all next time.